Hi, you guys. Good morning. I hope you guys had a really great weekend. We are going to continue our geometry unit today, and we are going to have a few lessons on triangle congruence. We're going to use the Khan Academy again, and we are also going to be doing your quiz during the video lessons. Okay, so take out a piece of paper, make sure you have something to write with, and follow along. We're going to go ahead and get started.
Let's talk a little bit about congruence. Congruence. And one way to think about congruence, it's really kind of equivalence for shape. So in algebra, when something is equal to another thing, it means that their quantities are the same. But if we're now all of a sudden talking about shapes and we say that those shapes are the same size and shape, then we say that they're congruent. And just to see a simple example here, I have this triangle right over there. And let's say I have this triangle right over here. And if you are able to shift this triangle and rotate this triangle and flip this triangle, you can make it look exactly like this triangle, as long as you're not changing the lengths of any of the sides or the angles here. But you can flip it, you can shift it, you can do and rotate it. So you can shift, let me write this, you can shift it, you can flip it, and you can rotate. If you can do those three procedures to make these the exact same triangle, to make them look exactly the same, then they are congruent. And if you say that a triangle is congruent, and let me label these. So let's call this triangle A, B, and C. And let's call this D, what do we call it? X, Y, and Z. X, Y, and Z. So if we were to say, we make the claim that both of these triangles are congruent. So if we say triangle ABC is congruent, and the way you specify it, it looks almost like an equal sign, but it's an equal sign with this little curly thing on top. Let me write it a little bit neater. So we would write it like this. If we know that triangle ABC is congruent to triangle XYZ, that means that their corresponding sides have the same length, and their corresponding angles have the same measure. So if we make this assumption, or if someone tells us that this is true, then we know, for example, that AB is going to be equal to XY. The length of segment AB is going to be equal to the length of segment XY. And we could denote it like this. And I'm assuming that these are the corresponding sides. And you can see it actually by the way we've defined these triangles. A corresponds to X, B corresponds to Y, and then C corresponds to Z right over there. So side AB is going to have the same length as side XY. And you can sometimes, if you don't have the colors, you would denote it just like that. These two lengths these two line segments have the same length. And you can actually say this, and you don't always see it written this way. You can also make the statement that line segment AB is congruent to line segment XY. But congruence of line segments really just means that their lengths are equivalent. So these two things mean the same thing. If one line segment is congruent to another line segment, that just means the measure of one line segment is equal to the measure of the other line segment. And so we can go through all of the corresponding sides. If these two characters are congruent, we also know that BC, we also know the length of BC is going to be the length of YZ, assuming that those are the corresponding sides. And we could put these double hash marks right over here to show that these two lengths are the same. And then if we go to the third side, we also know that these are going to have the same length, or the line segments themselves are going to be congruent. So we also know that the length of AC is going to be equal to the length of XZ. Is going to be equal to the length of XZ. Not only do we know that all of the corresponding sides are going to have the same length, if someone tells us that a triangle is congruent, we also know that all the corresponding angles are going to have the same measure. So for example, we also know that this angle's measure is going to be the same as the corresponding angle's measure. And the corresponding angle is right over here. It's between this orange side and this blue side, or this orange side and this purple side, I should say, and between the orange side and this purple side. And so it also tells us that the measure of angle is this BAC, BAC is equal to the measure of angle YXZ. Measure of angle, let me write that angle symbol a little less like a measure of angle YXZ. YXZ. We could also write that as angle BAC is congruent to angle YXZ. And once again, like line segments, if one line segment is congruent to another line segment, it just means that their lengths are equal. And if one angle is congruent to another angle, it just means that their measures are equal. So we know that those two corresponding angles have the same measure. They're congruent. We also know that these two corresponding angles have the same measure. And I'll use a double arc to specify that this has the same measure as that. So we also know that the measure of angle ABC is equal to the measure of angle XYZ. And then finally, we know that this angle, if we know that these two characters are congruent, that this angle is going to have the same measure as this angle, as its corresponding angle. So we know that the measure of angle ACB is going to be equal to the measure of angle XZY. Now what we're going to concern ourselves a lot with is how do we prove congruence? Because it's cool, because if you can prove congruence of two triangles, then all of a sudden you can make all of these assumptions. And what we're going to find out, and this is going to be we're going to assume it for the sake of kind of an introductory geometry course, that this is an axiom or a postulate or just something that you assume. And let me actually just write this down. So an axiom, a very fancy word, postulate, also a very fancy word. It really just means things that we're going to assume are true. An axiom is sometimes, there's a little bit of distinction sometimes where someone will say an axiom is something that's self-evident, or it's just, it seems like a universal truth that is definitely true and we just take it for granted. You can't prove an axiom. A postulate kind of has that same role, but sometimes you can say, well, let's just assume this is true and see if we assume that that's true, what we can derive from it, what we can prove if we assume it's true. But for the sake of an introductory geometry class, and really in most of mathematics today, these two words are used interchangeably. An axiom or postulate, just very fancy words for things that we take as a given, things that we just will assume. We won't prove them. We will start with these assumptions, and then we're just going to build up from there. And one of the core ones that we'll see in geometry is the axiom or the postulate that if all of the sides are congruent, or if the lengths of all of the sides of the triangle are congruent, then we are dealing with congruent triangles. So it's sometimes called the side-side-side postulate or axiom. We're not going to prove it here, we're just going to take it as a given. So this literally stands for side-side-side, side-side-side. And what it tells us is if we have two triangles, and so let's say that's another triangle right over there, and we know that corresponding sides are equal. So we know that this side right over here is equal in length to that side. We know that this side right over here is equal in length to that side right over there. And we know that this side over here is equal in length to this side over here. Then we know, and we're just going to take this as an assumption, and we can build up off of this, we know that they are congruent, that these two triangles are congruent to each other. I didn't put any labels there, so it's kind of hard for me to refer to them, but these two are congruent triangles. And what's powerful there is if we know all of the corresponding sides are equal, then we know they're congruent, and then we can make all of the other assumptions, which means that the corresponding angles are also equal. So that we know that that's going to be congruent to that, or have the same measure. That's going to have the same measure as that, and then that is going to have the same measure as that right over there. And to see why that is a reasonable axiom or a reasonable assumption or a reasonable postulate to start off with, let's start with one triangle. So let's say I have this triangle right over here. So it has that side, and then it has that side, and then it has that side right over here. And what I'm going to do is see if I have another triangle that has the exact same side lengths, is there any way for me to construct a triangle with the same side lengths that is different, that can't be translated to this triangle through flipping, shifting, or rotating? So we assume this other triangle is going to have a side that's the same length as that one right over there. So I'll try to draw it like that, roughly the same length. We know it's going to have a side that's that length, so it's going to have a side that's that length. Let me put it on this side just to make it look a little bit more interesting. So we know it's going to have a side like that. So I'm going to draw it roughly the same length, but I'm going to try to do it at a different angle. And we know it's going to have a side, that looks like that. It's going to have a side that looks like that. And so I'll put it right over here. It's about that length right over there. And so clearly this isn't a triangle. In order to make it a triangle, I'll have to connect this point to that point right over there. And really there's only two ways to do it. I can rotate it around that little hinge right over there. If I connect them over here, then I'm going to get a triangle that looks like this. I'm going to get a triangle that looks like this, which is really just a flipped, am I visualizing it right? Yeah, just a flipped version. You could rotate it a little bit back this way, but then you'd have the magenta on this side and the yellow on this side, and then you could flip it vertically, and then it would look exactly like this. Our other option to make these 2 points connect is to rotate them out this way. And then the yellow side is going to be here. The yellow side is going to be here, and then the magenta side, is going to be right over here. And that's not magenta. The magenta side is going to be just like that. And if we do that, then we actually just have to rotate it. We just have to rotate it around to get that exact triangle. So this isn't a proof, and actually we're just going to start assuming that this is an axiom, but hopefully you see that it's a pretty reasonable starting point, that if all of the corresponding sides of two different triangles are equal, then we know that they are congruent. We're just going to assume it is an axiom that we're going to build off of, that they are congruent, and then we also know that all of the corresponding angles are going to be equivalent.
Okay, you guys, so we just watched a video on triangle congruence, and we are going to go ahead and do your first quiz question. Okay, so on your piece of paper, I want you to write down this question number 1. So you'll write number 1, and then you are answering this question. If we know two triangles are congruent, what do we know about the triangles? So what does it mean to be congruent? Okay, and now we are going to move to video number 2.
We now know that if we have two triangles and all of their corresponding sides are the same, so by side, so if the corresponding sides, all three of the corresponding sides have the same length, we know that those triangles are congruent. What I want to do in this video is explore if there are other properties that we can find between the triangles that can help us feel pretty good that those two triangles would be congruent. So side works. What about angle? So let me do that over here. What about angle? So what I'm saying is if, let's say I have a triangle like this, like I have a triangle like that, and I have a triangle like this, and if we know that this angle is congruent to that angle, if this angle is congruent to that angle, which means that their measures are equal, and that angle is congruent to that angle, can we say that these are two congruent triangles? And at first case, it looks like maybe it is, at least the way I drew it here. But when you think about it, you can have the exact same corresponding angles having the same measure or being congruent, but you can actually scale one of these triangles up and down and still have that property. For example, if I had this triangle right over here, it looks similar, and I'm using that in just the everyday language size. It has the same shape as these triangles right over here, and it has the same angles. That angle is congruent to that angle. This angle down here is congruent to this angle over here, and this angle over here is congruent to this angle over here. So all of the angles in all three of these triangles are the same. The corresponding angles have the same measure. But clearly this triangle right over here is not the same. It is not congruent to the other two. The sides have a very different length. This side is much shorter than this side right over here. This side is much shorter than that side over there. And this side is much shorter over here. So with just angle, you cannot say that a triangle has the same size and shape. It does have the same shape, but not the same size. So this does not imply congruency. So angle, angle, angle does not imply congruency. What it does imply, and we haven't talked about this yet, is that these are similar triangles. So angle, angle, angle implies similar. So let me write it over here. It implies similar triangles. And similar, you probably are used to the word in just everyday language, but similar has a very specific meaning in geometry. And similar things have the same shape, but not necessarily the same size. So anything that is congruent, because it has the same size and shape, is also similar, but not everything that is similar is also congruent. So for example, this triangle is similar to all of these triangles are similar to each other, but they aren't all congruent. These two are congruent if their sides are the same. I didn't make that assumption, but if we know that their sides are the same, then we can say that they're congruent, but neither of these are congruent to this one right over here because this is clearly much larger. It has the same shape, but a different size. So we can't have an AAA postulate or an AAA axiom to get to congruency. What about side, angle, side? So let's try this out. Side, angle, side. So let's start off with one triangle right over here. So let's start off with a triangle that looks like this. I have my blue side, I have my pink side, and I have my magenta side. And let's say that I have another triangle that has this blue side. It has the same length as that blue side. So let me draw it like that. It has the same length as that blue side. So that length and that length are going to be the same. It has a congruent angle right after that. So this angle and the next angle for this triangle are going to have the same measure. They're going to be congruent. And then the next side is going to have the same length as this one over here. So that's going to be the same length as this over here. So it's going to be the same length. And we don't know, and because we only know that they have that two of the corresponding sides have the same length, and the angle between them, and this is important, the angle between the two corresponding sides also have the same measure. We can do anything we want with this last side on this one. We can essentially, it's going to have to start right over here. You could start from this point, and we can pivot it to form any triangle we want. But we can see the only way we can form a triangle is if we bring this side all the way over here and close this right over there. And so we can see just logically that if for two triangles, they have one side that has the length the same, the next side has the length the same, and the angle in between them. So this angle, let me do that in the same color. This angle in between them, this is the angle. This A is this angle and that angle. It's the angle in between them. This first side is in blue, and this second side right over here is in pink. And well, it's already written in pink. So we can see that if two sides are the same, have the same length, two corresponding sides have the same length, and the corresponding angle between them, they have to be congruent. There's no other place to put this third side. So SAS, and sometimes it's once again called a postulate, an axiom, or if it's kind of proven, sometimes it's called a theorem. This does imply that the two triangles are congruent. So we will give ourselves this tool in our toolkit. We had the SSS postulate, now we have the SAS postulate. Two sides are equal and the angle in between them for two triangles, corresponding sides and angles, then we can say that it is definitely these are congruent triangles. Now what about, and I'm just going to try to go through all of the different combinations here. What if I have angle, side, angle? So let me try that. So what happens if I have angle, side, angle? So let's go back to this one right over here. So actually, let me just redraw a new one for each of these cases. So angle, side, angle. So I'll draw a triangle here. So I have this triangle. So this would be maybe the side. That would be the side. So let me draw the whole triangle actually first. So I have this triangle. Let me draw one side over here, and then let me draw one side over there, and this angle right over here, I'll do it in orange, and this angle over here, I will do it in yellow. So if I have another triangle that has one side having equal measure, so I'll use it as this blue side right over here. So it has one side that has equal measure, and the two angles on either side of that side, or at either end of that side, are the same. Will this triangle necessarily be congruent? And we're just going to try to reason it out. These aren't formal proofs. We're really just trying to set up what are reasonable postulates, or what are reasonable assumptions we can have as we kind of, in our toolkit, as we try to prove other things. So that angle, let's call it that angle right over there, is going to be, they're going to have the same measure in this triangle, and this angle right over here in yellow is going to have the same measure on this triangle right over here. So regardless, so I'm not in any way constraining the sides over here. So this side right over here could have any length. It could have any length, but it has to form this angle with it. So it could have any length, and it can just go as far as it wants to go. In no way have we constrained what the length of that is. Actually, let me mark this off too. So this is the same as this. So that side can be anything. We haven't constrained it at all. And once again, this side could be anything. We haven't constrained it at all, but we know it has to go at this angle. So it has to go at that angle. Well, once again, there's only one triangle that can be formed this way. We can say all day that this length can be as long as we want or as short as we want, and this one can be as long as we want or as short as we want. But the only way that they can actually touch each other and form a triangle and have these two angles is if they are the exact same length as these two sides right over here. So this side will actually have to be the same as that side, and this would have to be the same as that side. Once again, this isn't a proof. I'd call it more of a reasoning through it, or an investigation, really just to establish what are reasonable baselines or axioms or assumptions or postulates that we can have. So for my purposes, I think ASA does show us that two triangles are congruent. Now let's try another one. Let's try angle, angle, side. Let's try angle, angle, side. And in some geometry classes, and maybe if you have to go through an exam quickly, you might memorize, okay, side, side, side implies congruency, and that's kind of logical. Side, angle, side implies congruency, and so on and so forth. I'm not a fan of memorizing it. It might be good for time pressure. It is good to sometimes even just go through this logic. If you're like, wait, does angle, angle, angle work? Well, no, I can find this case that breaks down angle, angle, angle. If these work, just try to verify for yourself that they make logical sense why they would imply congruency. Now let's try angle, angle, side. Let's try angle, 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 side. So once again, let's have a triangle over here. It has some side. So this one's going to be a little bit more interesting. So it has some side. That's the side right over there. And then it has two angles. So let me draw the other sides of this triangle. I'll draw one in magenta and then one in green. And there's two angles and then the side. So let's say you have this angle. You have that angle right over there. Actually, I didn't have to put a double because that's the first angle that so I have that angle, which we'll refer to as that first A. And then we have this angle, which is that second A. So if I know that there's another triangle that has one side having the same length, so let me draw it like that. It has one side having the same length. It has one angle on that side that has the same measure. So it has a measure like that. And so this side right over here could be of any length. This side of here could be at any length. We aren't constraining what the length of that side is, but whatever the angle is on the other side of that side is going to be the same as this green angle right over here. So for example, it could be like that, and then you could have a green side go like that. It could be like that and have the green side go like that. And if we have, so the only thing we're assuming is that this is the same length as this, and that this angle is the same measure as that angle, and that this measure is the same measure as that angle. And this magenta line can be of any length, and this green line can be of any length. We in no way have constrained that. But how can we form any triangle that is not congruent to this? Because at the bottom line is, this green line is going to have to touch this one right over there, and the only way it's going to touch that one right over there is if it starts right over here. It starts right over here because we're constraining this angle right over here. We're constraining that angle. And so it looks like angle, angle, side does indeed imply congruency. So that does imply congruency. So let's just do one more just to kind of try out all of the different situations. What if we have, and I'm running out of a little bit of real estate right over here at the bottom. What if we tried out side, side, angle? So once again, draw a triangle. So it has one side there, it has another side there, and then I don't have to do those hash marks just yet. So one side, then another side, and then another side. And what happens if we know that there's another triangle that has two of the sides the same and then the angle after it? So for example, it would have that side, just like that, and then it has another side, but we're not constraining the angle. We aren't constraining this angle right over here, but we're constraining the length of that side. So let me color code it. So that blue side is that first side. Then we have this magenta side right over there. So this is going to be the same length as this right over here, but let me make it at a different angle to see if I can disprove it. So let's say it looks like that. Or actually, let me make it even more interesting. Let me try to make it like that. Let me try to make it like that. So it's a very different angle, but now it has to have the same angle out here. It has to have that same angle out here, so it has to be roughly that angle. So it actually looks like we can draw a triangle that is not congruent, that has the same, two sides being the same length, and then an angle is different. For example, this is pretty much that. I made this angle smaller than this angle. These two sides are the same. This angle is the same now, but what the byproduct of that is that this green side is going to be shorter on this triangle right over here. So these aren't, you don't necessarily have congruent triangles with side-side angle. So this is not necessarily congruent, not necessarily, or similar. It gives us neither congruency nor similarity.
There is to know about all three angles and all three sides. If you have certain conditions met, you can still say
Okay, you guys, so you are ready for your second quiz question. Here it is. What are 4 different ways that you can prove that two triangles are congruent? 1 is side, side, side. What are 3 others? Okay, and now we are ready for your last lesson.
What we have drawn over here is 5 different triangles. What I want to do in this video is figure out which of these triangles are congruent to which other of these triangles. And to figure that out, I'm just over here going to write our triangle congruency postulate. So we know that 2 triangles are congruent if all of their sides are the same, so side, side, side. We also know they are congruent if we have a side and then an angle between the sides and then another side that is congruent, so side, angle, side. If we reverse the angles and the sides, we know that's also a congruence postulate. So if we have an angle and then another angle and then the side in between them is congruent, then we also have 2 congruent triangles. And then finally, if we have an angle and then another angle and then a side, then that is also, any of these imply congruency. So let's see, or congruent triangles. So let's see what we can figure out right over here for these triangles. So right in this triangle ABC over here, we're given this length 7, then 60 degrees, and then 40 degrees. Or another way to think about it, we're given an angle, and a side. 40 degrees, then 60 degrees, then 7. And in order for something to be congruent here, they would have to have an angle, side given, at least, unless maybe we have to figure it out some other way. But I'm guessing for this problem, they'll just already give us the angle. So they'll have to have an angle, side. And it can't just be any angle, and side. It has to be 40, 60, and 7. And it has to be in the same order. It can't be 60 and then 40 and then 7. If the 40 degree side if one of its side has the length 7, then that is not the same thing here. Here the 60 degree side has length 7. So let's see if any of these other triangles have this kind of 40, 60 degrees, and then the 7 right over here. So this has the 40 degrees and the 60 degrees, but the 7 is in between them. So this looks like it might be congruent to some other triangle, maybe closer to something like angle, side, angle, because they have an angle, side, angle. So it wouldn't be that one. This one looks interesting. This is also angle, side, angle, so maybe these are congruent, but we'll check back on that. We're still focused on this one right over here. This one we have a 60 degrees, then a 40 degrees, and a 7. This is tempting. We have an angle, and a side. But the angles are in a different order. Here it's 40, 67. Here it's 60, 47. So it's an angle, and side, but the side is not on the 40 degree, on the 60 degree angle. It's on the 40 degree angle over here. So this doesn't look right either. Here we have 40 degrees, 60 degrees, and then 7. So this is looking pretty good. We have this side right over here is congruent to this side right over here. Then you have your 60 degree angle right over here, 60 degree angle over here. It's a little, might not be obvious because it's flipped and they're drawn a little bit different, but you should never assume that just the drawing tells you what's going on. And then finally, you have your 40 degree angle here, which is your 40 degree angle here. So we can write down that, and I'll do it, let me think of a good place to do it. I'll write it right over here. We can write down that triangle ABC is congruent to triangle. Now we have to be very careful with how we name this. We have to make sure that we have the corresponding vertices map up together. So for example, we started this triangle at vertex A. So point A right over here, that's where we have the 60 degree angle. That's the vertex of the 60 degree angle. So the vertex of the 60 degree angle over here is point N. So I'm going to go to N. And then we went from A to B. B was the vertex that we did not have any angle for. And we could figure it out. If these two guys add up to 100, then this is going to be the 80 degree angle. So over here, the 80 degree angle is going to be M, the one that we don't have any label for. It's kind of the other side. It's the thing that shares the 7 length side right over here. So then we want to go to N, then M, and then finish up, N, M, and then finish up the triangle in O. And I want to really stress this, that we have to make sure we get the order of these right, because then we're kind of referring to, we're not showing the corresponding vertices in each triangle. Now we see vertex A, or point A, maps to point N on this congruent triangle. Vertex B maps to point M. And so you can say, look, AB, the length of AB is congruent to NM, so it all matches up. And we can say that these two are congruent by angle, side, by AS. So we did this one right over here is congruent to this one right over there. Now let's look at these two characters. So here we have an angle, 40 degrees, a side in between, and then another angle. So it looks like ASA is going to be involved. We look at this one right over here. We have a 40 degrees, 7, and then 60. And you might say, wait, here the 40 degrees is on the bottom, and here it's on the top. But remember, things can be congruent if you can flip them. If you can flip them, rotate them, shift them, whatever. So if you flip this guy over, you will get this one over here. And that would not have happened if you had flipped this one to get this one over here. So you see, these two you have, let me just make it clear. You have this 60 degree angle is congruent to this 60 degree angle. You have the side of length 7 is congruent to this side of length 7. And then you have the 40 degree angle is congruent to this 40 degree angle. So once again, these two characters are congruent to each other. And we can write, I'll write it where I have some, I'll write it right over here. We can say triangle DEF is congruent to triangle. And here we have to be careful again. Point D is the vertex for the 60 degree side. So I'm going to start at H, which is the vertex of the 60 degree side over here. It's congruent to triangle H, and then we went from D to E. E is the vertex on the 40 degree side, kind of the other vertex that shares the 7 length segment right over here. So we want to go from H to G. H, G, I, and we know that from angle, side, angle, by angle, side, angle. And so that gives us that character right over there is congruent to this character right over here. And then finally we're left with this poor chap, and it looks like it is not congruent to any of them. It is tempting to try to match it up to this one, especially because the angles here are on the bottom, and you have the 7 side over here, angles here on the bottom, and the 7 side over here. But it doesn't match up because the order of the angles aren't the same. You don't have the same corresponding angles. If you try to do this little exercise where you map everything to each other, you wouldn't be able to do it right over here. And this over here, you know, it might have been a trick question where maybe if you did the math, if this was like a 40 or 60 degree angle, then maybe you could have matched this to some of the other triangles, or maybe even some of them to each other. But this last angle in all of these cases, 40 plus 60 is 100. this is going to be an 80-degree angle right over here. They have to add up to 180. This is an 80-degree angle. This is an 80-degree angle. If this ended up by the math being a 40 or 60-degree angle, then it could have been a little bit more interesting. There might have been other congruent pairs, but this is an 80-degree angle in every case. The other angle is 80 degrees. So this is just a lone, unfortunately for him, he is not able to find a congruent companion.
Okay, you guys, so now you are ready for your last quiz questions. I'm going to go ahead and show you what they look like. So for each of these quiz questions, I want you to tell me if the two triangles are congruent and by what postulate. Okay, so are the two triangles congruent and by what postulate? And remember, your choices are side, 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 okay, so your choices are side, side, side. Sorry, my S's aren't working very good this morning. So side, side, side. Let's see if I can write this a little bit better. And actually, maybe I'll just type it. Okay, so side, 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 angle, side, angle, side, angle, and angle, angle, side. Okay. Remember, one that does not work is side, side, angle. And if we flip that around, you can see that that would be a word that we would typically not want to say. And so that's how I always remember that these four work right here. Okay. And that this one doesn't. Okay. There is no swearing in triangle congruency. So for question number 3, you are saying yes or no. Are these two triangles congruent and by what postulate? And then you have question number 4. Are these two triangles congruent and by what postulate? Question number 5. Are these two triangles congruent and by what postulate? Question number 6. Are these two triangles congruent and by what postulate? And the last one, question number 7, are these two triangles congruent and by what postulate? Okay, remember that in a triangle, all 3 angles have to add up to be 180 degrees. Okay, so that might be a piece of information that you need to use as you are working through the rest of this quiz. So with that said, I want you guys to have a really good day, and your next new lesson will be on Wednesday. So I will see you on Wednesday. When you turn this into me, I will correct it. And if you missed any or you need some more practice on this, I will let you know. So have a great day, you guys.